Recording's rolling. It's Wednesday, May 13th. We're gonna get you guys the stats packet. We're going to take a few days to do a little bit of stats. A lot of times I'll just right before the quantum journal so that helps make quantum mechanics make a little bit more sense to right, how particles can exist probabilistically. A lot of you guys turned in the quantum journal yesterday. If you haven't turned in the quantum journal yet, then just turn it by the end of the week. If you missed something, you can, of course, go catch the videos. They're all uploaded to Google Classroom. Catch it if you need. Today's senior exam day for science. So seniors get set up their final exam. Laptops, guys, be ready to be turning in your laptops, especially if you're a senior. You only got a couple days left, but junior too, start thinking ahead a little bit. Like, all right, what's the last day I really need my laptop? Yeah.
Can I turn them in today?
Your laptop? Yeah. So after class, yeah, after class you can bring it to me and huh? Where your laptop is? Oh, well, guess you got 1 week to find out. Yeah. Right, so let's look at now this is really just introductory. Of course, if you take a stats class, you're going to learn more than like 3 pages of stuff, right? But you'll get some core concepts here and be able to also think statistically, right? So I hope you guys get something out of this, right? And so I've got some formulas up here. I'll explain those in a minute, right? But the first 3 questions I have samples of data. It looks like we have heights of dogs, heights of people, and heights of cats. You guys see that? So okay, dogs, people, and cats. Right? Now, just from life experience, you can have an idea of like, okay, dog height. Aren't there all different size dogs? There's little tiny chihuahuas. There's big Great Danes. There's all in the middle. Okay. So a lot of variability. Right? You guys, which generally taller, dogs or people? People. Yeah, people are generally taller, but there's a lot less variability, isn't there? Right, people are usually about, like by the time adulthood, about 5, 6 feet tall, somewhere there, but a lot less variability. Right? Oh, but what about cats? Right, are cats generally like the shortest height out of all 3 of these groups? Right? But there's almost no variability at all for house cats. I mean, unless you start growing like tigers and stuff, you probably wouldn't want to adopt one of those. So, so how can we make sense of this data? And yeah, there's only a sample of like 5 here, 5 here, 5 here. Right? Realistically, you probably want sample size of hundreds to get something more realistic. And there's 2 main features we're going to be looking at in terms of numerical value. I got the mean average, which is something that you guys have done in this class. You guys have probably done since elementary school. You guys know how to find a mean average, right? You just add up all values and divide by the number in the set. Right? So that's not too bad. But this next concept is probably new to most of you guys. This is called standard deviation. And it measures the spread of the data. Remember I was talking about that variability? I was saying dogs have a lot of variability in the size, people less so, and cats almost no variability at all. Right? This is how we're going to quantify variability. Right? And I see some curves here. You guys see these 3 curves? Okay. Yeah. Okay. Actually, hang tight on that. All this goes together. Think about the order I want to do this. So, okay. Let's go ahead and start solving these. So, dogs. Now, there are different versions. If I have some version, you have a different version.
That's okay.
So we have different numbers, but we're all using the same process here. So let's find average dog height. Okay, so I got 75 centimeters tall, 83 centimeters, 92, 99, and 116. Okay. Now, if I add up all those and I divide by 5 for 5 dogs, then to give me the mean. Let's try this. Okay. You guys go ahead and do your numbers. You guys are calculating your numbers? Yes, we all have different numbers. Yeah. Okay. So these are centimeters. So I'll say X bar, like the average, is the sum total of the heights divided by 5 for 5 dogs. Okay. And I have my mean height. Okay. Now, if I were to assume that these 5 dogs are somehow representative of the largest sample. Oh, yeah, okay. Okay. All right. Yeah, if you want to make some inference about a wider population, ideally you'd have lots more dogs than 5. You'd probably want a few hundred, but that aside, it's good data. Okay. All right. Now, what about the standard deviation? Here, kind of put a curve together to represent this. Okay. Let's say you're looking at frequency on this vertical axis. I think I did this actually the other day, but it's worth seeing again anyway. Okay. and I'll put like the height of a dog on this axis. Okay? And let's say instead of having 5 dogs, you have like hundreds of dogs. You start to make a bar chart, like a histogram, a bar chart. Okay? And there's some medium-sized dog, and actually there's a lot of dogs that show up as the medium-sized dog. Maybe you have like 10 dogs, so like medium-sized. Okay? And then here's a little bit shorter than that. Well, almost as many dogs, but maybe a few fewer. Okay? And then now this will start to taper off. Maybe do something kind of like this, right? And then you got just a few very 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 short dogs. And then who's taller than the average? Well, the taller you get, the fewer dogs there are going to be that are taller than average, right? So we might complete a bar chart like that. Okay. Now, if you stand back and look at it, because I just made a bar. First of all, is that okay? That would make sense. That if you look at the medium size, there are a lot of medium size, and then there are fewer short, fewer very tall. That makes sense, right? If we stand back and look at this, and this is true for a lot of data, it'll eventually create what's called a bell curve. Okay, this is bell curve data. Right? So from now on, we're going to ignore the bars and just look at the curve. You guys see the curve peak right here? That, okay. Now, guys, this value right here. Okay, so somebody tell me. I want to make sure that you guys are following the story I'm telling you guys. I'm pointing to a value right here. Conceptually, what does this value right here represent? Yeah, the mean or the median. Yeah, in this case, it would be the same thing because it's a nice symmetrical bell curve, right? Yeah, so some kind of average value, right? Which I'll usually designate x bar. Let me say or. Sometimes you'll say mu. Right? So I might use those symbols interchangeably in the next few days. But if you take this task class, I think they use x bar for like smaller samples and mu for like larger populations. But anyway, okay. So these can both represent average, like an average value. Right? So the mean in this case. Okay. Right. Now, how about how spread out is the data? Well, do you guys see how the middle of the curve is like an upside down bowl? Do you see that upside down bowl? But look at the tails. Isn't the tail of this curve right here and here? It's kind of like you turn the bowl back right side up. You see that?
It's concave up.
Ah, concavity. Right, concavity. Okay. In fact, you might know this then. Okay. There's a name, a mathematical name for the point where it switches concavity. And what is that point called?
Inflection.
Inflection point. Yeah, here, I'll spell it up. Good call. Inflection point. Okay, one on the side and one on that side, where the concavity switches. Okay. Now, guys, if the data was more spread, if there was even more variability in heights, wouldn't this curve be really spread out and these inflection points would be pushed way out here? Okay. Or can you guys imagine by the time we get to house cats, all house cats are pretty much the same size, that there's going to be very little variability. Therefore, these inflection points are going to be squeezed way in. Just measure that, right? So if you go from this mean average to this inflection point, and it's measurable, so it's the same on both sides. Okay, this gap, this distance here from here to here, okay, is called one standard deviation, and I'm going to designate that with this Greek letter sigma for standard deviation. Okay. And well, just I have two different symbols for average. I also have two different symbols for standard deviation. I might use the lowercase f, although s's are kind of tricky because you don't want to make it look like a 5, but leave that. Again, if you take a stat 5, you might use the f for smaller samples and the sigma for larger populations, but I might use those kind of interchangeably for today, next few days. Okay. You guys hear that? Right. To tell you something about how spread out is the data. Now, how can we find out just from a set of numbers how spread out is the data? And that is what this formula is for right here. You guys do this formula? Now, this formula is actually a process. Here, I'll walk you through the process, point it out, and then I'll walk through it with you guys with the numbers. Okay. So this says you take each individual value. You guys see that x sub I? Okay. So in this case, we got 5 sample heights. So we'll have to do this for 5 different numbers. I'm going to subtract the average. That's what x bar is, the average. Okay. I'll take that difference and I'll square that difference. Okay. Now, here's a little side thought that maybe will matter too. Because anytime you square a number, it always becomes what? Starts with a P. Positive. Like positive, right? If you square a number, it doesn't always become positive. Right. And that leads to the next step. Guys, what does the sigma mean to do?
That's the total.
Yeah, to add them up, right? Right. You guys know that, right? If you see that summation, it means to add them all up. Okay. Notice I'm adding up a bunch of squared differences. Okay. So like, if I had not squared the differences, let's see if you guys get this too. Here, sorry, it's being blurry. I'm just gonna write this on paper because I have double focus in there. Okay. So I'm saying here the standard deviation says S. Right, equals. Right. It says to take the summation, so I'm gonna add up each individual value minus the average BM squared. That okay, yeah. All right, yeah, check summation. And then no, there's more to this formula, but I want to pause and just see if you guys get this concept. Okay. Guys, what if I had not squared the differences first? What if I just added up all the differences? I would necessarily always get what number? Guys, okay. Some numbers are above average, some are below average. If you subtract all the averages, sometimes you're above, sometimes you're below. Okay. And then if you were to add up all those differences, just straight up differences, you would always get what number? 0. Yeah, because you would always get 0. Okay. Okay. Maybe that's one reason you think, well, okay, well, if I square all the differences first, right, it makes it positive. I mean, there's more of that story too. Okay. But if you forgot to square them first, you would always get 0, and that would not be helpful at all. Okay. Anyway, but there's more to the story. Next step we're going to do is we're going to divide by the number in the set minus 1. This is called degrees of freedom. So in this case, we have five dogs for 5 heights. I'm going to do 5 minus 1 to get 4 here. There's a whole story behind that. I'm just going to run with it. Right? And very last step is to take the square root of this whole thing. Okay. You can sort of think that kind of like undoing the square before, but basically that. So you guys see this is going to be a process, right? It's going to be a process. So let's do this with these 5 dogs. Now I have a particular paper. You guys have different numbers than I do, but here's my 5 dogs. All right, you guys ready to do this with your 5 dogs? All right, we're all going to do this. So I'll say the standard deviation for my 5 dogs is, well, I'll take first dog is this tall. These are all in centimeters. Subtract my average. My average was 93 centimeters. I'm going to square that difference. Then plus, because that's what summation means. I'm going to say plus. Now, my second dog is this tall. Subtract the average, square. Plus, my third dog is this tall minus the average, square. Plus, fourth dog minus the average, squared. Plus, fifth dog minus average, squared. Okay. So I took every individual dog height, I subtracted the average value, which was 93 centimeters over and over. Squared all those differences. Now I've added them all up. Okay, so now I'm up to the sigma section. Okay. Now after I do that, I still got a couple more steps. I'm going to divide by. Well, guys, I have 5 dogs here, right? So 5 minus 1 would be 4. Right? And actually, that'll be true for all of us because I gave everybody 5 dogs. Okay. And there's one last step. Guess what's the very last step? Square root. That's it. You got to square root this whole expression. Okay. And that will tell me, because remember what we're trying to find. I don't want you guys to lose track of the story. That tells me how far from this average to this inflection point, which effectively tells me how spread out is that data for that bell curve. Okay? Okay. Like, what's the variability among dog heights? It's called standard deviation. So I need to plug this all in my calculator. I'm going to chunk this down to the smaller parts. Let's do that minus that squared. Okay. Right, you guys are calculating your numbers at the same time? Okay. Here, I'll throw it in the middle so that we got square root of 994. Okay, I'm looking at this value here. Right. This would also be in centimeters. All these numbers are centimeters, including the standard deviation. It's going to be in centimeters. And so now I can go over to this box and I can write that in. Centimeters, great. Think of that kind of like a plus or minus value, like a plus or minus. Like if we go back to my bell curve, right? I know the average dog height is, well, this height right here, according to my numbers. And if I do plus or minus my standard deviation, that covers most of the bell curve. And then all that's left are these tails here, these very, very tiny dogs, and these very, very large dogs. Right? But otherwise, my average plus or minus that standard deviation covers most of the dogs. Okay. Make sure you guys are caught up. Okay. Do you guys also have a number in this box? You guys still working on that? Still working? All right, here, make sure. Okay, yeah, you got it. Okay, yeah, looks about right. Yep. Ooh, sometimes areas.
I would put on my list. Also, but. What else? And here.
One thing I would do is insert a close pencil there, so guys by 4. And then the other close pencil. I think this one is my favorite, like watch you. Like the other modify.
I always just visit one that's out of town. I got the same one.
And then.
I was there
There was
first and second.
Insert one more.
This is the Haunting Joe. The what? Haunting Joe. Oh, it's lovely.
Okay, actually, I'm about to show you guys another video too, but let's go with that. Also, yeah. That calculator. Alright.
I don't really care for this one.
Guys doing here. Alright, guys getting the number there? Get the number? Okay. Hey guys, so I want to show you guys a different way to do this. That's gonna be a little bit faster. So for all this other data. Alright, you guys ready to see a faster way? Yeah, here, show of hands. How many guys are taking stats or in the stat class or have taken stats? Anybody taking stats? Oh, okay, so this is new to you guys. All right. So yeah, if you have a graphing calculator, there's a way to do that. There's also a way with this model calculator. Now I know everybody has one of these within reach, right? Okay. Guys, everybody pick up this model. Make sure you have a TI-30X2S. Everybody have this one? All right, search it. All right, now it's turned on. You guys turn it on. No, guys, do this. Hit second. You guys hit second right here. Second. And see this button says data, and right above it says stat. Well, now that you hit second, it's going to pull up stat. Okay. And it should pull up one variable. Okay. Guys, does anybody not have this on their screen right now? So everybody has this on their screen. Is that right? Okay. Hit what? Now you have one variable. Hit enter. Okay. And the word stat will pop up on your screen. So the word stat should be on your screen at this point. Does anybody not have the word stat on their screen? So everybody has the word stat on their screen. Okay, now hit the button that says data. So it just says data. And it'll say X1. All right, how you guys doing? How you guys doing? So everybody has X1 on their screen right now? Everybody's good? Everybody's good? Right. Now we're going to start plugging in these dog heights. Now, I remember my dog heights are these 5 numbers here. So my short dog was this tall. Whoops. There he goes. Okay. Okay, did you guys type in your first dog height? Okay. All right, so it's... okay, so clear this out. You just hit data. Hit this data key. Okay. Okay, and it'll pull up X1. So, okay, does anybody not have X1 on their screen? Okay. So I typed in my first dog. Then scroll down. It'll say frequency 1. Now, if you have lots of dogs that were that height, then it would be really convenient to override that. So I have 13 dogs that height, right? But here I only have 1. So I'm just going to leave frequency at 1. Scroll down again. X2, the second dog, is this tall. So type in your second dog. Scroll down, frequency, yeah, there's only one of those dogs. Scroll down. X3, type in your third dog. Scroll, scroll. Fourth dog. Scroll, scroll. Fifth dog. Okay, now I have my 5 dog heights plugged into the calculator. How about you guys? Does anybody not have their 5 dog heights plugged into the calculator? So everybody has their, yeah. Oh, yeah. Yeah, you got all 5. Right? Okay. All right, so everybody's got all 5 dogs plugged in the calculator. Everybody has all 5 dogs. Right. Now, see this key that says StatVar? StatVar? Click that one. Click that one. Calculate. Hey, N is 5. Oh, that means I have 5 dogs. That's true, right? Everybody have 5? Make sure. Just in case there wasn't data in there from before. Scroll to the right. X bar. Hey, is that average? My average dog height? 93 centimeters. Oh! That's what I got by adding up all the dog heights and dividing by 5. This did it for me. Are you guys getting matching numbers too? All right. Scroll to the right one more time. What is this? 15.7. Oh! That's that number! It gave you the standard deviation. So you should get what you got before. Guys, that was a whole process. Did we just do a whole process where I took differences and squared them, add them up, and divide by n-1, took the square root? That was a whole long process. This calculator just did it all for me. Right. Now, the one to the right of that, with the sigma, we're not going to use that one. That's for population standard deviation, so ignore it. It's a slightly different number. See that? It's like 14 point something. Okay, we're just going to use the S. So 15.73. Okay. All right, so you guys good. You guys good. All right, now let's do this for the next set of heights, which it says the heights of 5 people in centimeters. So let's go to that. So I'm going to clear out this data. Well, actually, I'll just override what I already have. So I'll go to X1 and put in my first person. Scroll. Second person. Scroll. Third person. Scroll. Fourth person. Scroll. And fifth person. Okay, so got that. I go back to stat var. Yep, I have 5 people. Scroll to the right. Average height is this many centimeters. Yes, that looks approximately correct. It's kind of in the middle of all those values. That was right. I can believe that. Scroll to the right again. And now I get the standard deviation. Okay. So think of that as your plus or minus value on the height that would cover most of the people. Okay. Finally, let's do this for cats. So go back to data, plug in my first cat height. Scroll, second cat, scroll, third cat, scroll, fourth cat, scroll, fifth cat. Okay, then stat var. Yep, there are 5 cats. Yep. The average cat height. Yeah, that looks believable. That's kind of the middle of those numbers. And then standard deviation. Oh, that's a very tiny standard deviation. There's almost no variability at all for the cats. Okay. Are you guys getting the same story? Okay. Again, we all have different numbers. We have different dogs, different people, different cats. Right? But the basic story should be the same. That there's a lot of variability in dog height, and there's almost no variability in cats, and people are kind of in the middle. Right? You guys see that? Makes sense. Okay. Now we're ready for these bell curves. Now I showed you guys how to construct one bell curve, like from a histogram. Is that okay? Let's pair these bell curves to these populations. So, okay. And there's 2 pieces of evidence you can use. Guys, the further to the right the bell curve is, tells you what? Here.
If they're all.
Yes, if they're taller. Yeah. Right. And I see the peak of the curve could represent like the average value. Right. So yeah, the further a bell curve is to the right, the average individual is being taller and taller. Right. Another piece of data is like how spread out is the data. Now, do you guys notice that the more spread out it is, it's also flatter at the same time? Right. The reason for that is like if you add up all the area underneath the bell curve, it adds up to 100% or 1. So 100% of each respective population. So the areas of these curves ideally are the same as each other. Okay. But if you spread it out more, that consequently makes it shorter. Okay. Can I get the idea? Okay. Okay. So putting all that together, which curve do you think is on the far right?
Even.
Yeah. We got so it's labeled humans or people. Okay. Yeah. Because not only is that the height, the tallest average height value, but also it has the medium type variability, right? It's not as spread out as this middle curve. It's not as tight as this curve on the left, right? Which curve do you think is right in the middle?
Dog.
Dogs. We're gonna label this dogs. And which curve is on the left? Cats. There you go. Right. Both because there's the shortest average height value, but also because there's hardly any variability at all. For house cats. Right, you guys see how that makes sense? All right. All right, guys ready for the next part? All right, so go down here. New concept. It's called a z-score. So see where it says z equals x minus mu over sigma? I'm going to write that a little differently too. So it says x or x of I, something to see it, minus mu over sigma. Right. Another way to write this is x minus s. No. I'm so sorry. X bar. There we go. That looks better. X bar over s. That's what I meant. Okay. So sigma or s represent the standard deviation. and this mu or this x bar represent the average. Right. So we're doing using two different sets of notation here, but okay. So what was and this x of I is some individual value. So I could measure your height with meters. Actually, this will probably be tomorrow's activity where I have you guys break out some meter sticks to measure each other's heights. It's just going to take us a few days to go through this packet. Okay. And so this could be like your height in centimeters, and then compared to like everybody else in the population, something like that. Okay. Okay. So what z-score is going to tell you effectively is how many standard deviations an individual is from the mean within their population set. Right? Like if you can read the music of this equation and understand it before we start throwing in numbers and throwing this in the calculator, this will make a lot more sense. Okay? So let's say you took your height and you subtracted the average from the height. Couldn't that right away, if you got a positive or a negative value, tell you if you're above average or below average height into that? Right? And if this came out to 0, what would that represent? It would mean you were exactly what? Exactly average. Great. Now, okay, so great. I know if I'm above average or below average for height, whatever. Then, if you divide by the standard deviation size, you're effectively getting a count of how many standard deviations. That's really what z-score is. It's the number of standard deviations from the mean. Okay. And if this value is negative, then it's below average, and if it's positive, it's above average. Okay, but furthermore, it'll tell you like how many standard deviations. Okay, right, you guys get that too? Okay, so let's try this for. Okay, I got a couple of dogs here, a couple of people, and a couple of cats here. Okay, all right, so I'm just gonna run the numbers on my paper. You guys have a different paper. So my first dog is 60 centimeters tall. So let's try this. This is number 4. Okay. So remember, I'm using this model here. Z-score is the individual value minus the average over the mean, or sorry, over the standard deviation net. Okay. So Z-score for number 4. Okay. I got a 60 centimeter tall dog. I know the average dog was 93 centimeters. I found that before. I'm going to play off that. Okay. And then the standard deviation size is 15.73. Right, these are all in centimeters. Centimeters. Okay. Let's see what the calculator says is this. 60 minus 93 over 15.73. Okay. I'm looking at negative 2.1. Okay. All right, and so this is multiple choice. You can know right away if you got it. I'm seeing that value. Okay. All right. All right. Are you guys okay with that so far? All right, so here, I'm gonna knock out the rest of these. So number 7, I'll just stay on the dogs for now. Number 7 over here. I got a dog that's this many centimeters tall. And the average was also that many centimeters tall. So doesn't this have to be 0?
Yeah.
0? Okay, so yeah, if you are exactly average on some metric, then your z-score is 0 for that metric with respect to your population. Number 5, Z for, okay, now we're moving on to humans. I have a human that is this many centimeters tall. Actually, this looks like this person's also average. Oops. So it's a different standard deviation. Okay, because I'm on the people now. Okay, but the z-score is still 0 because I happen to pick an average person. Okay, so now I have a z-score for that person. How about a human who's 200 centimeters tall? This is number 8. Z for number. So I have 100. A 200 centimeter tall person. 200 centimeters tall. The average person is 178 centimeters, according to that data from before. Standard deviation is this many centimeters. Let's take my plus or minus value. See what is this? At 2.45, something like that. Yeah, there you go. All right, jot that right there. Boom, z-score. Right. And let's do this for cats. Finally, got some cats. Right, so number 6. I have a cat that's this many centimeters tall. The average was this many centimeters. And the standard deviation is this many centimeters. It's like the plus or minus factor. Let's see. Right, the z-score on this cat is negative. I got a sports cat. Oh, here, I meant to ask you guys this too. Guys, centimeters over centimeters gives you what unit? Would that be unitless? No unit? Right. Guys, all these z-scores have no units on them. That'll be important later. Okay, so right now we're just getting some numbers. Yeah, so that was z-score on that cat. And finally, last cat, number 9. I have a cat that's this many centimeters tall. Subtract the average. Divide by the standard deviation for cat height. Okay. And let's see, that minus that over that. Okay, I'm getting that z-score. That z-score. Yep. That is a multiple choice answer. Boom, 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 boom. Okay. How about you guys? Are you guys getting multiple choice answers on your papers? Alright, so it's working out. It's working out for everybody. Alright, everybody's working out. Alright. Okay. So a couple more things today. Is if you flip the page to the next side. Okay. Now, actually, tomorrow I'll probably go over this side, but here, I want you guys to see this graphic right here. Okay. You guys see this bell curve? Guys, take a look at this bell curve. Okay. Now, guys, this bell curve is uniform. This is in terms of standard deviations. You guys see right in the middle is mu for average. Okay. You guys, look at this axis down here. See, it goes from -3 to 3.
No.
Those are like z values. Okay. So, guys, plus or minus 1. Oh, look at this point right here. Now, you guys told me earlier today, but see if you guys remember. Guys, what is the name of this point right here called? Inflection point. It is. Guys, this is an inflection point. See where it switches from concave down the middle to concave up on the tail? Okay. And look at that. That aligns exactly with one standard deviation. Exactly like I told you guys it would. You guys see that? Okay. Now, guys, watch this. If you start with the average of anything, guys, this is really general. This could be anything. This could be heights of cats or people or dogs or trees or anything that's normally distributed. If I go plus or minus 1 standard deviation, remember before I said, well, that would cover most of the population? Now you guys can see exactly how much. Because how much of the population does that cover? 68%. Does everybody see 68%? Well, let's go plus or minus 2 standard deviations. How much does that cover? Is that about... Go ahead and add those numbers up. What are you guys getting? Plus or minus 2 standard deviations. That covers what percent? 95%? That sounds right. Right? How about, guys, if you did plus or minus 3 standard deviations, is that like almost the entire population at that point? Yeah. So guys, if you take a stats class one day, and I hope you do, because this is one of these classes I took that really changed my view of so many things in the world. Okay. There's something called the 68, 95, 99.7 rule. Right. Which corresponds to plus or minus 1 standard deviation, plus or minus 2 standard deviations, plus or minus 3 standard deviations. Right. As to what percent of the entire population that would cover for some particular metric. Yeah. Right. And at that point, guys, if you're out on these tails, like plus or minus 4 standard deviations, you're either like freakishly short or freakishly tall for, if we're talking about height. Hey, you see that? Hey, do you guys remember just a few days ago we were finishing that quantum mechanics journal? I told you if scientists claim they discovered a new particle, like the Higgs boson or something. Do you guys remember what the standard deviation standard was? Yeah, it was called 5 sigma. You have to be so far out on this tail, it's called 5 sigma. What that really means is that if they're studying all these particle collisions, that if the data was to be truly random, it's like, oh, the Higgs boson doesn't really exist. It's just like all the data seems to indicate it. So, but it's just like winning the lottery or something. That the chance of that happening would be like being so far out on this tail that it actually ends up being, I think it's approximately 3 out of 10 million, which is like less than 1 in a million chance, right? So roughly on par with winning the lottery. So when scientists come out and say, you see a newspaper headline that scientists say they've discovered a new particle, they're so sure because it'd be on par with winning the lottery if they had not, but it's all statistical. Okay. Okay. And the other thing I want to show you guys today, hey guys, this will be the last thing today. is if you flip the packet over and look at the very last page. You can see the very last page, right? Oh, look, I have a bell curve again. Do you guys see how the left side could go all the way up to the average, and then the right side looks like everything that's above average? That's what it's trying to get at here. Guys, this tells you how much of the bell curve is covered up to that particular value, right? And what's on the far left of the table? What letter is this right here? Z. Oh, so for example, let's see if you guys remember this from a few minutes ago. If you have a z-score of 0 on SOMetric, which I think may have shown up earlier on your packet, that means what again?
Your average.
Your average. You guys, if you're average on SOMetric, that means you're greater than what percent of the population? 50. Ah, aren't you greater than 50 and you're less than 50? That would put you exactly at average. Let's take a look at the z table here. Guys, go to here. Here's a z-score of 0.0. And if you go across, sorry, it's not focusing super well, but you got this in front of you anyway, right? If you go across this column, you can get more granular. It's 0.00, 0.01, 0.02. You guys get, you can get more granular, right? So let's go to just 0.00, and my finger is covering up a value. But you guys just told me what value that should be, and it represents how much is shaded up to this particular z value. And what value should I be covering up with my finger? 50%. Look at that. As a decimal, that would be 0.50, of course. You can see it. Ah, you guys just told me why that would be. Didn't you guys just tell me that?
Yeah.
Aha. You guys good? Guys see it? Right. Now, guys, let's go way out on the tail. Let's go. Actually, let's stop right here at a z-score of 1. Guys, if you have a z-score of 1, you're above average somehow, right? Should that put you maybe about actually we can get it from here. Should be this 50% plus this 34%. Guys, what is 50% plus 34%? Is that 84%? 84%? So if I go to z-score of 1, I should get about 84%. Hey, it is 84%. Actually, it's 84.13%. Oh, okay. Let's go way out on the tail. Let's go as far as we can go. Guys, what if you had a z-score of like 3.4? You're almost 3.5 standard deviations out. At that point, guys, if you're way out here at 3.5 standard deviations, are you like one of the tallest people in the world? Maybe like 7 feet tall? You're probably 7 feet tall at that point. You're taller than 99.97% of the population. Ah, you guys see how this graphic is coming together?
Wait, how tall is your 0.997?
Oh, I'm just making something up. But yeah, you'd probably be 7 feet tall. Right. I'm just kind of spitballing numbers just to get the idea, right? Yeah, you're probably 7 feet tall at that point. If you're taller than 99.97% of the population, right? You know, and top like 1 in 10,000. Right? Right. How about the other way? What if you were like 3 standard deviations below average? Let's see. Could that be a z-score of like -3? Right. And at that point, if you're talking about height, you'd be so short that you are only taller than, well, as a percentage, you can call it 0.13%. Yeah. So there might be a few people shorter than you, but not too many people. Okay? You guys see that? Okay. So I think that's quite a bit today. So recap what we've done. Right. You guys, of course, know how to take a mean average. You guys probably have been doing that since elementary school in this class. Add up the values, divide by the number. Okay. Standard deviation. You use this whole journey right here. It will tell you how spread out the data is. You guys know how to plug the data into this calculator, so it will automatically give you average and standard deviation. You can find an individual, person, dog, cat, tree, whatever, right? And apply this formula. So subtract the average, divide by standard deviation to get you a z-score. And then, finally, last thing, is you can use that z-score to tell you where you rank within a population on some particular metric. Okay? Right? Now, tomorrow, when you guys come to class, I'll have you guys pull out some meter sticks and measure each other's heights. Right? And then there's a day 3 of this. Probably get to the end of the week. All right, so that is a good pause point today.